In the first part of the lecture, we'll have a look at some graphs of exponential functions. An exponential function is of the form f of x, or y, equals a to the power of x. A is called the base, and x is called the index, or the exponent. The graph currently displayed is f of x is equal to 2 to the power of x. So we start with the number 2, and as x increases, you can see the graph curves steeply upwards. So when x is equal to 1, we have 2 to the power of 1, which is 2. When x is 2, 2 to the power of 2 is 4, and so on. There are some characteristics which all exponential graphs have in common, and one of them is they cut the y-axis at y equals 1. And there's a very good reason for this. As you know from the rules of indices, a number to the power of 0 is equal to 1. So obviously, where it cuts the y-axis, x is equal to 0. So we have 2 to the power of 0, which is 1. The exponential graphs curve upwards very steeply as x increases. And in fact, if there were a race to get to infinity, the graph of an exponential function would get there much more quickly than any polynomial. No matter what the order of the polynomial is, the exponential graph would get to positive infinity more quickly as x increases. As x decreases and becomes negative, you can see that the curve approaches the x-axis, but it never actually touches the x-axis. So the x-axis is an asymptote to the graph of an exponential function, which is in the form of a number to the power of x. Obviously, if we were to have some constant term, for example, f of x is equal to 2 to the x minus 1, it would cut the x-axis, but then the line y equals negative 1 would be the asymptote to the graph of the function. So what do you think will happen as we increase the value of the base? So how about if we went from 2 up to 4? Well, you can see there's a very sharp increase in the steepness of this curve. Of course, as the base gets larger, the curve will get steeper and steeper. So it will go all the way up to 10, and you can see it's now curving very sharply upwards. That's going to head off to infinity really quickly. What do you think will happen if the base is equal to 1? Shall we have a look and find out? So we'll slowly come back down to 1. You can see it's curving less steeply upwards. It would still win the race to infinity though. Let's go back down to 1. Okay, so we have a horizontal line going through y equals 1. And that's to be expected because 1 to the power of x, no matter what value of x takes, will always give us 1. I wonder what will happen then if we let the base decrease so it's still positive but it's less than 1. Let's have a look. It's 0.9, 0.8, 0.5. Well, that's interesting because if we just go back to positive 2, they look very similar, don't they, in terms of how steep the graphs are. So that's f of x is equal to 2 to the x, and that's f of x is equal to 0.5 to the x. So what about if we go down to 0.1? So f of x is 0.1 to the power of x. F of x is equal to 10 to the x. So they look as though they're curving upwards by the same amount, but they're just in different quadrants of the graph. So do you think it's possible that they're a reflection in the y-axis? What do you think about that? Well, in fact, the answer is yes. It is a reflection in the y-axis. And the mathematical reason for that is that if we have f of x is equal to 2 to the power of x, when we consider the reciprocal of 2, well, we'll have a half, won't we? The reciprocal of 2 is just 1 over 2, which is a half. But that's the same as writing 2 to the power of minus 1. Now, if we raise that to the power of x, we're going to have 2 to the power of minus 1 to the power of x, which is 2 to the power of minus x. So that's going to be a reflection in the y-axis. So for the reciprocal function, the graph will be a reflection in the y-axis of the, in this case, the whole number function 2 to the power of x. So if we take the case of a base a is equal to a half, it will be a reflection in the y-axis. If you're still not convinced by that, we can put another graph on here to illustrate this more clearly. So let's have another graph, and we'll call this g of x. And g of x in this specific case is a half to the power of x, which is 2 to the minus x. So you can see that they're a perfect reflection of each other. And as we change the value of the base, you'll see the reflections changing. So when we get to a base of 4, the red curve is showing 4 to the x, and the blue curve is the reciprocal, which is a quarter to the power of x, or 4 to the minus x. And if we go all the way up to 10 there, 10 to the x and 1 over 10 to the power of x. So you can see they're a reflection of each other in the y-axis. Okay, lastly then, let's consider the case where we have the graph of an exponential function. Let's go back to 2 to the power of x again, and we want to find the value of x for which f of x is equal to 7. So we can solve this using logarithms, which we'll look at a little bit later in the lecture. But for now, we'll consider a graphical solution to this problem. So we want to solve the equation 2 to the x is equal to 7. You won't be assessed on this, but let's have a look at some slides and I'll explain exactly how we could estimate the solution to a problem like this. We want to find the value of x such that 2 to the power of x is equal to 7, and we're going to use the graph to solve that problem.
To summarise what we saw in the animation then, y equals a to the power of x is an exponential function. A is called the base, and x is called the index, or the exponent. All exponential graphs of the form y equals a to the power of x pass through the point 0, 1. That is, they have an intercept of 1 on the y-axis. Also, exponential functions win the race to infinity. They'll get there faster than the polynomials or any other function. We should also remember that y equals a to the x will have this characteristic form. So as x increases, y will approach positive infinity, and the x-axis is a horizontal asymptote. In the case where we have a negative exponent, the reciprocal case, y equals a to the minus x is the same as 1 over a to the power of x. This will head off to infinity as x becomes more negative. Again, of course, it passes through 0, 1, and the x-axis is a horizontal asymptote to the graph of the function. As we mentioned at the end of the animation, we sometimes want to solve an equation of the form a to the x equals some number. So let's have a look at how we can estimate the solution using a graphical method. So what we're going to do is we're going to draw a graph to estimate the solution to 2 to the x equals 7. You won't be asked to do this in any assessment, but it's useful to be able to know how to do this. In fact, we'll look at how we solve this type of problems using logarithms a little bit later in the lecture. Alright, so what we'll do to start with is we'll just draw up a table of values. So we'll take x as 0, 1, 2 and 3 and we'll write in the y values. So y is equal to 2 to the power of x. So in the case when x is 0, y will equal 1. It'll equal 2 when x is 1. Y will equal 4 when x is 2. And it will equal 8 when x is 3. We can just pop those points on our axes there. So we're going to have 0, 1, 1, 2, 2, 4, which is about there. And at x equals 3, y is going to equal 8, so that will be about there. We can now sketch in our curve, which will go something like this. So there we have the graph of y is equal to 2 to the x. We want to find the value of x such that 2 to the x is equal to 7. So we can draw a horizontal line across there at 7. So that's y equals 7. And we then want to drop a vertical line down here like this. So it looks as though it's going to be just under 3. So we could estimate that x is going to be approximately equal to 2.8, say. That would be our guess or our estimate of what the solution is going to be. Okay, now have a go at the multiple choice question.